Hello students, welcome to my channel again. In the previous lecture we have discussed about various types of pumping and then active medium and about optical resonator. And we are now ready to learn some basic laser principles. And the first ever laser that I am going to discuss with you in today's lecture is the ruby laser. So this laser, if we remember that in case of laser, the three essential components of a laser are active medium, pump and optical resonator. So first of all, we will describe its construction. Then we will discuss the various concepts involved in the working of the ruby laser. So let me draw the diagram of the basic diagram of a ruby laser. So it consists of a rod of ruby, which is a naturally occurring pink colored stone. So this rod is of pink color, and the composition of this rod is ruby is actually Al2O3 and it is doped with Cr2O3. And the concentration of this is usually of this 99.95%, and concentration of Cr2O3 is very small, it is 0.05% only. Now so this is a ruby rod doped with chromium ions. So what we do, since it is in the solid form, we polish this ruby rod from both of the sides, and one of the side is partially polished, therefore it represents as partially reflecting mirror. So it means we need not to require or add extra mirrors in ruby rod ruby laser, because this is actually a solid form and it is a transparent medium, and we can use its end faces as mirrors themselves. So we polish it partially, and the other face is highly polished so as to make it totally reflecting. Okay, then this ruby rod is wrapped with a glass tube, and this glass tube is filled with xenon gas. So this is a spiral type of glass tube and it is filled with a xenon gas. So I have already given a link of very short and informative video in which the working of optical flash lamp and along with a ruby rod was given. That was my lecture number 4, if I remember it precisely, in the chapter of lasers. You can see its link in the description part of that lecture. So it was, I will give the link of that video in this lecture also, so you can easily see how it works. Now what is there? This tube is connected through the electrodes to a voltage source. This is a high voltage battery, and this is a resistance which controls the current. This is a key, and parallel to this we place an appropriate capacitor. Why this capacitor is always needed whenever we want to make a flash lamp? The circuit will always contain a capacitor. So let us say this is the capacity of capacitor. This is the resistance of the resistor. This is key. This is a battery of EMF capital E, and it is filled with xenon gas. And since this is the partially reflecting mirror, let me say that this is the axis of the rod. So the light will come out of the partially reflecting mirror, and it will be parallel to the axis of the rod. So there are three components of the laser. One is the active medium, other is the pump, and third one is optical resonator. So let me show you these three components in this diagram. So this combination of, this is a ruby rod. I would just mark this here. This is a ruby rod. Ruby is actually nothing but aluminum oxide. It's a naturally occurring stone. This is a ruby rod doped with the chromium oxide. So this doped ruby rod, it acts as laser medium. So this ruby rod is acting as a laser medium. Out of this, the chromium plus 3 ions, they form the active medium. And each individual ion can be called as active center. And this aluminum oxide, it does not take part directly in the laser action, and therefore it is a supporting medium. So kindly remember that the light that comes out of the ruby rod, it is due to the chromium plus ions. So why we do not take therefore a rod of chromium? So for that you should remember that this chromium oxide is opaque, while on the other hand aluminum oxide is transparent. So we have to use it in the doped form of with the aluminum oxide. So next, it means now you have seen what is the active medium. So first component you might have observed in this diagram. This rod is the laser medium, out of which aluminum oxide is the supporting medium and chromium ions are active centers, or you can say chromium oxide is the active medium. Pump. So pump is the energy providing device which will achieve the population inversion, and it will maintain it for a desired period of time. So now you can see this xenon filled glass rod along with the capacitor, battery, resistance and key. Whole of this circuit, including this spiral glass tube which is filled with this xenon tube, it is acting as an energy pump. So now you have observed the second component of the laser in this diagram. The third component, optical resonator. If you go to the definition of optical resonator, it is a system of two mirrors, one of which is partially reflecting and other is totally reflecting. Now here we do not use separate mirrors in case of ruby rod. I have already told it earlier in this at the start of this lecture. The end faces of the ruby rod themselves act as mirrors. So these are very well polished. It is due to the reason that this rod is transparent, so we need not to use extra mirrors in this case. So one of the rod face is highly polished and it becomes totally reflecting. You know that reflecting surfaces are very good mirrors. And this face is partially polished, therefore it will become partially reflecting. So these two end faces of the ruby rod, they act as optical resonator. So therefore the construction part of this is over, and you have seen active medium, pump, optical resonator as well as supporting medium in this laser. Now let us discuss how it works. So I can erase this space now, and I will be erasing this space. I assume that you might have noticed whatever was drawn here. Okay, let me draw the energy diagram of this laser. So these are the energy level. This is the energy level diagram of chromium 3 ions in the ruby rod. So here actually we have two bands. This energy level I will call it to be E1, and this energy level is called to be, it's actually energy band E2. This is E3. These are broad bands, and there are very narrowly spaced. I would draw it just slightly below. Very narrowly spaced two metastable states, M1 and M2. These are very narrow. The energy difference between both of these metastable states is very small. So this is the energy level diagram. So this is actually, if I draw the energy scale on the right hand side, this is actually just this is here 1.25 electron volt. This is slightly near 2.5 electron volt, and this is somewhere here is 3.75 electron volt. So if we insert the key in this circuit, we are now going to discuss the working of the laser. So from here to here I will draw parallel analogy so that you will be clear of the concepts. So kindly remember that you have studied out, of course, it in your lower classes, that a capacitor blocks DC. However, this statement is incomplete. Please remember, only fully charged capacitor, only a fully charged capacitor blocks DC. If a capacitor is uncharged, it will not block DC. It will allow the flow of current till it is fully charged. Once it is fully charged, after that it will stop the current in the circuit if the current is DC, direct current. So please remember this, that capacitor blocks DC only when it is fully charged. Then what will happen if capacitor is uncharged? So please remember, an uncharged capacitor acts like zero resistance wire. So therefore, when key will be inserted in this circuit, then a current will flow from the battery, positive terminal of battery. I am talking about the conventional current, therefore it will start from positive terminal of the battery. And when it will reach at this junction, let me call this junction as A and this junction as B. When this current will reach the junction A, then at point A, the division of current will not take place. Why? Because this portion is coming to this electrode and this portion of the wire is coming to this electrode, and these two electrodes are in the tube, and this tube is filled with xenon gas. And please remember that all gases are bad conductor of electricity when these are in atomic or molecular form. So this is an important part. So therefore, this xenon gas initially acts as a resistor of resistance infinite. So when the current is coming from the battery, it will reach at junction A. At junction A, one of the branch which is connecting to this spiral glass tube, it is through the xenon gas. This spiral glass tube will act as a infinite resistance, and other branch which is traveling towards the capacitor, since the capacitor is uncharged, it will act as a zero resistance. So what is going to happen? The whole of the charge supplied by the battery will travel toward the capacitor. As a result, this plate of the capacitor will become positively charged. Similarly, this plate will become negatively charged, and due to the flow of charge, the potential difference between the plates of the capacitor will start increasing, and this tube will not get any charge. So a stage will reach when this capacitor will get fully charged. When this capacitor will get fully charged, it will block the flow of charge from the battery to it. So at that stage, when it is fully charged, this current in the whole circuit, this current will become zero. When this current will become zero, the voltage drop by this capacitor, which is I into R, it will also become zero. Now, when the capacitor was charging, then the potential difference during the charging across this will be smaller than the EMF of this battery because of some voltage drop across this resistance R. However, when the capacitor is fully charged, since I is 0, so IR is equal to 0, so when capacitor is fully charged, there will be no voltage drop across this capacitor. So kindly take this into account. There will be no voltage drop across this capacitor, and as a result, this potential difference across this capacitor will be exactly equal to EMF. So there will be no voltage drop, whole of this voltage, because this branch and this branch are in parallel, and in parallel potential remains same. So the potential across this branch will be E. So therefore the potential across capacitor will also be E. So when the capacitor will be fully charged, so whatever is the EMF of this battery will be across this capacitor. So it means what we have to take into account while we are using this capacitor, we must remember this capacitor must not break down at a voltage which is equal to the EMF of the battery. So capacitor must be capable of withstanding this voltage. This is the first thing engineering wise, since again my target audience is engineering students, so they must take, so this is some sort of a manufacturing parameter, so we must take into account. Another thing that we must remember is that the EMF of this battery must be sufficient to ionized xenon gas. Means in case of xenon gas, since all the orbits are fully, it is a noble gas, so therefore all the orbits are fully filled. So its ionization potential is of course very high. I do not know its value. You can search it from the Google. So the EMF of this battery, which will be equal to actually the potential difference across the capacitor when it is fully charged, must be able to create the ionization of this gas. So when this will happen, that the capacitor is fully charged, then because of the potential, this potential will appear across the electrodes of the tube. And earlier the potential was small, it was not capable of charging or ionizing the gas. Now because IR is 0, so therefore this battery's complete potential will appear across the electrodes, and this is capable of ionizing the gas. And when the gas will ionize, then kindly remember, I have written here a statement here that all gases are bad conductors of electricity in atomic and molecular form. But contrary to that, the ionized gases are very good conductors of electricity. So this is another property. So same gas, xenon gas. So actually this is very interesting thing. Capacitor uncharged was low resistance, and fully charged capacitor is high resistance. Similarly, neutral gas is high resistance and ionized gas is low resistance, and these properties are appearing contrast. So it means when the capacitor will become charged, it will cause the ionization of the gas. So this gas, when it will become ionized, its resistance, it will reduce from infinity to very small value, R dash, let us say. Kindly remember, this R dash is different from this. So R was the capacitance while charging. So when the capacitor will charge, it will charge at this rate, Q equals Q naught into e raised to power 1 minus e raised to power minus t upon RC. It will charge at this rate, according to this equation, where R is this resistance. However, when it is discharging through this xenon gas. So its discharging equation will be Q equals Q naught. Q naught will be same in both of the cases, e raised to power minus t upon R dash C. So this R dash is actually the resistance offered by the ionized xenon gas. So obviously this time constant and this time constant will be different. So because in both of the, during the charging and the discharging time, the resistances that come into play are different. Therefore the capacitor will charge at a different rate and discharge at a different rate. Since this is usually high resistance and this is very low resistance, so it can be concluded from this that capacitor will charge at a low rate and it will discharge at a high rate. And in fact we need this also, because in the previous lecture I have told you that the pump cycle is, the capacity of a pump is limited by the lifetime of the states which are involved in the excitation process. So this lifetime is of the order of 10 raised to power minus 8 seconds in case of normal excited states. So therefore whatever population inversion can be created, it must be done within a time frame of 10 raised to power minus 8 seconds or less. So for that we must require an instantaneous discharging of the capacitor. The capacitor may take a while for charging, but it cannot take so much time for discharging. It must discharge instantaneously, so that all of a sudden the atoms within the material are excited to in large number to the excited state, and a strong population inversion is created. So I think you might have got this point which I wanted to discuss with you. Now, so what is going to happen when this discharge will take place? It will produce a flash of light, and this flash of light will be available till the capacitor is fully discharged. When the capacitor is fully discharged, then its resistance will again become infinite, and when its resistance will become infinite, so this discharge will stop because of the flow of the current will be stopped, and the ionized gas which contains xenon ions and free electrons within the same tube, these free electrons will again recombine with the xenon ions, and again the gas will become neutral, and as a result its resistance will become infinity, and since the capacitor has fully discharged, its resistance will become zero again. Battery will again come into action, and it will start charging the capacitor again because of the help of the resistance R, and again a capacitor will be fully charged, it will again discharge, it will again produce a flash, that flash will again discharge the capacitor, and the process will continue till we keep the key K inside the circuit. The flashing of the flashing of this xenon tube will continue. So it will give you light in the form of pulses that you can very easily verify in the video link that I will give in the description part of this lecture. So next, what is going to happen? So I can erase this portion. So what is going to happen when this flash will take place? Then the discharge will take place, and when the discharge will take place, then xenon flash will produce polychromatic light. That polychromatic light will be of different wavelength, and due to the fact that these two E2 and E3 are energy bands, therefore this polychromatic light will be very easily absorbed, because this energy gap and this energy gap lies in the visible region. So the wavelength of the photons, average wavelength of photons, which is required for excitation from E1 energy state, which is the ground energy state, to E2 band, it is of the order of 6000 angstrom. So on the average, all photons whose wavelength, all photons which are emitted from the xenon gas. Kindly remember, when xenon gas will not produce during the discharge, the xenon gas will not produce photons of same wavelength. So certain xenon atoms will be ionized by certain energy, and it will be therefore different types of photons emitted during the recombination of electrons with the xenon ions. So please remember. So the polychromatic light will be absorbed by the medium. So average wavelength of the light which is absorbed during excitation from E1 to E2 is of the order of 6000 angstrom, and average wavelength of the light for excitation from E1 to E3 is of the order of 4000 angstrom. So now what happens that the transition, these two bands are very short lived, so the transition as well as M2 are allowed, and these transitions are non-radiative transitions. Therefore it means that no visible light will be emitted during the transition from E3 to M1 M2 or E2 to M1 M2, it will just raise the temperature of the material. So these two states are very short, very close to each other, and the population of both of these states start increasing with time. These are long lived, therefore lifetime of these two states is of the order of 10 raised to power minus 3 seconds. These two are short lived, their lifetime is of the order of 10 raised to power minus 8 seconds. So what will happen, I will again take that example which I am taking in all my lectures. So suppose this flash is taking 100 ions to E2 or E3 in a time of 10 raised to power minus 3 seconds. Sorry, 10 raised to power minus 8 seconds, which is the lifetime of both of these states. So when these, in the first cycle, 100 chromium ions will be excited to either E2 or E3. In the next cycle, 100 mole will go to E2 or E3, but the first 100 in the meantime might have come either to E1 or either to M1 or to M2 through non-radiative de-excitation. So because the lifetime is completed. So although the pump might have excited 200, but out of these 200 only 100 will be there and remaining 100 will come here. So in the after third cycle, the pump might have excited 300. Out of these 300, 200 will have already come here. Here it will remain 100. So this will continue, and since the ratio of the lifetimes of these two states is of the order of 10 raised to power 5, so it means this will continue until the pump, which I have assumed that its cycle time is of the order of 10 raised to power minus 8 seconds. So this process will continue until the pump has completed 10 raised to power 5 cycles. Since in one cycle it is just exciting 100 atoms or 100 chromium ions, so in 10 raised to power 5 cycles it will excite 100 into 10 raised to power 5 equal to 10 raised to power 7 chromium plus ions. This is just an example, just to make the things more convenient for understanding to you. So now when it will happen, since the chromium ions are coming to these states at different instances, so the first supply, when the cycles will be 10 raised to power 5, so the first supply of 100 chromium ions will have their time exactly equal to 10 raised to power minus 3 seconds. So these 100 chromium ions will de-excite from M1 M2 to, sorry, I must draw a oblique line. These will de-excite, these 100 will de-excite in spontaneous fashion. So all of these photons will have an energy equal to this. Since these two are very close to each other, let us say their average energy is E2 dash. So all of these photons will have approximately same energy, E2 dash minus E1, and these will be in different directions. So I have discussed in my previous lecture the working of the optical resonator. So out of all these photons which are traveling at angle different than the axis of the rod, these will be lost. Means this photons of this kind, these will be lost, but photons of this kind which are by just chance emitted parallel to the principal axis, these will be multiplied, and once it happens, then such kind of photons, when these will be traveling within the rod, they will gather more photons due to their collisions with the chromium ions on their way within the rod, and as a result I will call such kind of photons which are emitted parallel to the principal axis to be seed photons. So seed photons are themselves spontaneous, but when these travel within the medium, then due to collision they produce stimulated photons. So seed photons will start a process which I will show by vertical line, and it will produce photons parallel to principal axis and in only one direction, and that direction will be through the partially reflecting mirror. So this photon which is traveling in this direction, it will actually strike with the totally reflecting mirror again, come back, and eventually all the photons which are emitted parallel to the principal axis will come out only of the partially reflecting mirror. So initially seed photon will start the process, and it will be sustained by later on by stimulated photons, and these stimulated photons will travel in the same direction due to law of conservation of the linear momentum. Now here one thing may come in the mind of the students that this light, kindly remember the wavelength of the photons emitted during this fashion, it is of the order of 6943 angstrom, and the color perception is in the red region. So this light, when it falls on a substance or a screen, will give you the perception of red color because it lies in the red region of the visible spectrum. So one concept may come in the mind of certain students that we want to just get only one wavelength, and we do not want to get another wavelength, and therefore we must produce resonance of the photons, desired photons. Means I want to, let us say, take M1 to E1 standing wave formation should be there, but M2 to E1 standing wave formation should not be there. For that I have described a concept that you must choose the length of the optical resonator in such a way that lambda is equal to L is equal to n lambda by 2. This condition is satisfied by only one wavelength. Here actually this will not work. This condition works only when the two states are widely separated. Here the two states are very narrowly separated. It will not work. I would tell you why it will not work here. So both of these wavelengths will be actually amplified. So in the output we will get both actually two lines of slightly different wavelength, and the average wavelength of both of these lines is given here. It is 6943 angstrom. Why we cannot suppress one of the line? Its reason is very simple. If we draw the frequency response curve of any oscillator, it's of this part. So this is called actually line width or bandwidth, and this is the resonance frequency. And here I will, in LCR circuit, this was called as current. However, I am dealing with this optical device, laser. So here in the frequency response curve, the y-axis will represent the intensity. So what is going to happen for an ideal resonance circuit? The graph should be a delta function. Means whole of the intensity should be corresponding to only one frequency. In that case, we say that bandwidth or the line width is 0. However, for practical purpose, no response curve of any circuit or any amplifying device is always having 0 width. So it means if I have, let us say, one frequency corresponding to omega m1, let us say the angular frequency is this. Since this is the second frequency is very closely spaced, so it will be on the lower side. M2 is on the lower side, so it will be somewhere here. So if I draw the frequency of the photon to transition from M2 to G, let us say it is omega 2, then what is going to happen? The intensity of the light corresponding to omega 2 will not be 0, it will be only slightly less. And intensity of the light corresponding to omega 1 will be more. And if we deal with the ideal resonance circuit, then the intensity corresponding to one frequency will be maximum, and intensity corresponding to all other frequencies will be zero. So that will be the ideal resonance, but it is not the ideal resonance circuit or ideal resonance optical device. So whenever the states are actually closely spaced, then the intensity of light due to all the closely spaced lines will be accounted for, because all these will be very high. On the other hand, if we say, let us say this is the full width at half maximum, this we usually call to be line width, and if we say there is any frequency beyond that bandwidth, let us say it is somewhere here, so this is omega n, let us say, and omega n is at a large separation from omega 1, then you can see due to omega n, the intensity of the light that will come out will be very small, and it will be negligible. In that case, the concept of resonance will it will work with great efficiency. However, in case of these two closely spaced energy states, this is not going to happen, and we have to bear with that. So the output intensity will contain frequencies corresponding to both transitions from M1 to G or E1 and M2 to E1. So please remember this. So this is how this ruby laser will work. So now please remember, in case of a laser, we have four energy levels. One is G, other is LL, other is UL, other is E. So G and E are involved in pumping. E to UL non-radiative transition takes place, and UL to LL lasing action takes place. LL to G induced de-excitation takes place. Now remember this, that this E1 energy state is acting as our G level. Both E2 and E3 are the bands, and the pumping mechanism excites chromium ions, some of the chromium ions to E2 and some chromium ions to E3. So therefore collection of both of these bands, E2 and E3, both of these bands collectively play the role of E, this one. And the transitions from here to here and here to here, these are taking place, and both of these metastable states are involved in population inversion. So the collection of both metastable states M1 and M2 forms UL, and this population inversion is between ground level and M1 M2. So therefore ground level is itself acting as lower lasing level. So lasing action is actually emitted from M states to G state. So as a result, you can see that this LL role is being played by G. So therefore this scheme will become this kind of scheme, where G ground level is playing the role of lower lasing level. So it means it is a 3-level laser. Ruby laser is a 3-level laser, because in it this LL and G are not separate. These are just one level playing the role of two different levels. So it is a 3-level laser. This is the level 1, this is level 2, and this is level 3. Fourth level is missing. It is actually the role of fourth level, that is LL level, is being played by the G level. So this you should remember. Next, what we remember here, that the light that will be coming out of this laser, if I draw the graph between intensity of the output light versus time, then what will happen, as these photons will be emitted, the intensity of the light will increase, and eventually it will become constant. When it will become constant, it will be due to saturation. The maximum number of chromium ions that can be excited when it will achieve, then it will become, sorry, it will not be at maximum, it will remain constant for a while, and this is what we expect. Actually it will not happen in the case. This is something which we expect, that this will saturate after a certain instant of time when the chromium ions, the maximum number of chromium ions which can be actually excited by the pump have been achieved, then it will remain there for a while, and this will remain till the capacitor is discharging. Now when the capacitor will be discharged, then what is going to happen? The population inversion will become zero, and as a result this will match to horizontal axis, and till the time remember this this discharging will take place for time with R dash C. Till the time the capacitor will be charging, this should remain 0, and when the capacitor is fully charged, again the discharging will take place and you will get light for certain interval of time. So this region will be represented by RC, this will be R dash C. So it will be at different rate, it will be at this time will be different and this time will be different. However, actually when we experimentally observed, the graph between intensity and time was not of this type, it was of this type. This region for which the light is being obtained from the ruby laser is called optical pulse region. So for this the laser action is on, here it is off, again it is on, again it is off. Kindly remember that for whole of this time we have not switched off the pump. The pump is on, but still this light is not emitted continuously, it is emitted in the discontinuously. It is due to the fact that we need large number of photons going to E2 or E3 suddenly. For that we accumulate this energy for large amount of time by using the capacitor, and all of a sudden this capacitor gives whole of this energy to the chromium ions in the ruby rod, so that all of a sudden population inversion is created. So therefore the laser action will quench for some time during the discharging. When the capacitor is fully discharged and it is charging, during that time the laser action will remain quenched and the light will be pulsed in nature. However, we instead of getting a flat pulse, we got a pulse having peaks, and these peaks were of different heights. So this is called spiking in the ruby laser. This is one thing which is different that what we expected. Another that this graph showed deviation from the expected graph is that the intensity did not reach 0. It did not reach 0 during the quenching. It means there was some light during the quenching also. Let me give the answer to this portion. Instead of drawing the flat, I may draw it some curve. The intensity may decrease or increase. Let me first of all give the answer to this region. Answer to this fact, that why intensity does not drop to 0 when the capacitor is fully discharged and it is charging. During that time, the answer to this is that when the capacitor is fully charged, there will be still some chromium ions in the state M1 or M2. However, the total number of chromium ions in these states will be now smaller than the number of ions in the state Ln. As a result, there will not be population inversion. So therefore, since there is no population inversion, the number of atoms in the ground level are now more than the number of atoms in the upper lacing level. So we know that now this condition N2 greater than N1 is violated, and the condition that is existing now is that N1 is greater than N2. It does not mean that the de-excitation process of these atoms will stop. Actually these are not atoms, these are chromium 3 ions. Actually the de-excitation of these chromium ions will continue, but now the rate of spontaneous emission will be more than the rate of stimulated emission. So it means during this region you will get a weak beam of photons due to spontaneous emission corresponding from M1 M2 to G. So that is why this curve does not touch the x-axis or horizontal axis. So even during the quenching time we get a weak beam, very weak, difficult to observe beam of spontaneous light. Now, why there is no flat curve of a pulse? Why there are small sharp spikes in each pulse? So the answer to this is that whenever this flash is there, the flash remains there for a large amount of time, and during that time, so this is the time for which the flash remains on, and this is the time for which the flash remains off. So the time for which the flash remains on, it may create population inversion many times. Sometimes the population inversion may be due to, let us say, there are 80% atoms in M1, M2 and 20% here, and sometimes the population inversion may be, let us say, here are 60% atoms and here we have only 40%. It means the strength of the population inversion will be different at different intervals of time, and kindly remember the flash time is large than the time required to produce population inversion. As a result, during the time when the flash is available in the rod, the population inversion will be achieved and it will be destroyed many times. Corresponding to every formation of population inversion and its destruction, there will be small pulse. That small pulse will be called spike. The question now here comes that why it is different. Here it is somewhere the peak is more sharp and more in height or more intense than the other case. This is a less sharp and a more wide small pulse. The answer is that this ruby rod, it contains some impurities, and due to these impurities sometimes there may be different population inversion, and due to these you remember that please remember that these impurity centers, these act as color centers, and they have the property of absorbing the light from the visible region. So sometimes the population inversion will be of large magnitude and sometimes the population inversion will be of small amplitude. So this is the reason of the spiking in the ruby laser. So now I will summarize this article with you, that kindly remember, in this ruby rod is supporting medium, chromium ions are active medium, and this is xenon gas filled in a spiral glass tube along with a capacitor, battery, a resistance and a key act as a pump, and faces, these act as an optical resonator, and the light comes out parallel to the principal axis and through the partially reflecting face. It is a 3-level laser. The light is emitted due to 2 closely spaced metastable states. Exciter level actually contains 2 bands. The light of the laser has wavelength 6943 angstrom. It falls in the visible region, and in the red color perception, the output is not continuous, it is in the form of pulses, and each pulse contains large number of small pulses called spikes. Due to the reason, the pulse is due to the reason that there is a flash, and spikes are due to the reason that there are impurities in the ruby rod. And this will sum up my article for today. Hope you will enjoy this lecture. In the next lecture I will discuss with you the working and principle of helium neon laser. So till then I will stop here. Thank you. Thanks a lot.